So today we're going to talk about some identities called the double angle and half angle identities. So we are going to find an identity for sine of 2x. And what we're going to use is the identity we have from yesterday for sine of x plus y. I don't expect you to have this memorized. I don't either. So sine of x plus y is equal to sine x cosine y plus cosine x sine y. And the question is, how could you use that to get an identity for sine of 2x? So this identity works if you have sine of something plus something, right? How could you express 2x as something plus something?
X plus x.
X plus x, great. Does that make sense? And then what you do is you plug in x for x, and what do you plug in for y? X. So this becomes sine x cosine x plus cosine x sine x. And is sine x cosine x any different than cosine x sine x? No. So really what that is 2 sine x cosine x. So that is one of the identities. It's sine of 2x equals 2 sine x cosine x. And I told you that I would identify when identities were used in future calculus classes. This definitely comes up in Calc 2. It's kind of a specific application, but it is something I made my Calc 2 students memorize and use, and it does come up in there. It doesn't come up as often in Calc 1, but it could. Does that make sense? Okay. It is one that I might make you memorize, but if I do so, I'll tell you. Does that make sense? If I'm going to make you memorize stuff, I'll give you a list of what you have to memorize, so you'll just clear what you have to know. Okay, so we can use the same technique to find an identity for cosine of 2x. So the formula for cosine of x plus y is cosine x cosine y minus sine x sine y. And we're going to proceed in more or less the same manner. Cosine of 2x is the same thing as cosine of x plus x, right? And then from there, just do the same thing. What's the first term going to be? Cosine x times cosine x, right? Minus what comes next?
Sine x.
Minus sine x times sine x. And how could you write those a little bit more nicely? Cosine squared x, yep. Or cosine of x, the quantity squared, but that's what that means. Minus sine squared x. Okay, so that's one form of this identity. I left you a lot of space there for a reason because we're going to do a little bit more stuff with that, but does that part make sense? Okay. Okay, so here's what we're going to do. Another formulation of this identity is, one thing that could be nice is instead of having both cosine and sine, we only had sine or cosine. Does that idea make sense on the right side? So how could you change the cosines into sines? Can you change these cosine, that cosine squared?
Cosine of like x,
You have cosine squared x plus sine squared x equals 1, right? You could use that. Does that make sense? So if you're using that, what does cosine squared get replaced by? 1 minus sine squared. Minus sine squared x. Does that make sense? So what else would cosine of 2x be equal to? 1 minus how many sine squareds? 1 minus 2 sine squared x. So that was making the cosines into sines. What if I wanted to make the sines into cosines? So I'll leave the cosine squared alone, minus what would go in for sine squared. And be very careful, what do you have to have there? I was thinking parentheses, does that make sense? Because you replaced sine squared by something that has two terms, so all of a sudden you need parentheses there. And I think that ends up saying cosine of 2x equals 2 cosine squared x minus 1. Do you guys agree with that? Because that negative distributes. Okay, so there are 3 different ways to say the same thing. They're mathematically synonymous. And that's one thing that's tricky about trig, is that they're all, yes?
On a test or quiz, would you have to name all 3, or do you just want one?
No. I mean, maybe I would give you one and say, prove it equals the other. Does that make sense? Like, I might make you show that it's true using a Pythagorean, but this is probably one that I wouldn't specifically ask for on a quiz, or if I did, you could give any of them that was true. These 2 right here, they also often come up in calculus 2, but they're written a little bit differently. That's why I left you a lot of space so we could actually do that. The way that you see those in calculus 2 is they're solved for the sine squared or cosine squared, meaning they have that by themselves. So let's take the first one, just because it's good to know what you're going to actually need. Let's take cosine of 2x, which equals 1 minus 2 sine squared x. And let's get the sine squared x by itself. So what would you do first to get that sine squared x by itself? Subtract 1. Great. Cosine of 2x minus 1 equals negative 2 sine squared x, right? What's the next thing you would do? Divide by negative 2. So if I say negative 1/2 times cosine of 2x minus 1 equals sine squared x, does that make sense? And it's often written just a little bit differently. It's often written as sine squared x equals positive 1/2 1 minus cosine of 2x. And the reason that's useful for my calculus 2 students is it allows you to convert a squared into something that's no longer squared, which makes certain problems that they do quite a bit easier. But does the idea that you can solve for something else make sense? Okay, so, and the other one, if you were to solve it for cosine squared, you're going to get 1/2 1 plus cosine of 2x. So, but the other point is that those, the identities that we proved yesterday give you a whole bunch of different identities as well. It's like they're used to produce a lot of identities that are sometimes useful. Is that all right? Okay. So show me that this is true. Yeah. So start with the more complicated side, which pretty obviously is the right side, right? So we're going to start with 2 tan x over 1 plus tan squared x. And the identities that you have to be really, really good at are the Pythagorean ones. Those are really the most important ones. So it's sine squared plus cosine squared is 1, right? Sine squared x plus cosine squared x equals 1. How do you get the identity involving tangent? What do you divide by? Oh, yes, I can move it down. Sorry. Yep. I divide by cosine squared. And the reason that you think that is, okay, oh, if I have sine over cosine, that makes tangent, right? So that gives me the identity, tan squared x plus 1 equals secant squared x, right? And knowing how to sort of just derive these other Pythagoreans is probably the best way to remember them. Personally, I have to do the division in my head every single time because I don't have a great memory, like, at least for certain things. Who gave us what wedding present? No problem. Math equations, sometimes a problem. Husband, math equations, no problem. Where stuff is, big problem. So, okay. So then how does that help us in the context of this problem? What can we simplify quite a bit? The denominator, you can make that into secant squared. Your numerator got 2 tan x. Okay, so that was Pythagorean. And now at this stage, you're like, well, I can change them into sines and cosines, right? And since your final answer involves sine, it's probably a good idea. Does that make sense? So your numerator becomes 2 times sine over cosine. All that divided by 1 over cosine squared, right? This is one of those times when you really can't skip steps. You've got to show them to me. Like, I'm so sorry, but you have to write them down. Actually, I'm not that sorry. Sorry, not sorry. 2 sine x over cosine x times cosine squared x over 1. Does that make sense? And now what cancels? The cosines. One of the cosines from the numerator. So left with 2 sine x cosine x. And this is from example number 1. So if you walked in late, this is what we showed in example number 1. That equals sine of 2x, right? So it's a bit tricky because it involves recognizing that that's what you're seeing. Does that make sense? Okay. Alrighty. Is that okay? All right. So these kinds of questions, if I ask you to do, say, an identity on a test, what I'm probably going to do, because I haven't written your test yet, I'm probably going to do one question where you just use Pythagoreans and stuff. I'll probably do one question where you have to use some things that are on that list you're given. Does that make sense? Just to see if you can figure out which things from the list are appropriate to apply. So when you're working on your ALEX, I would suggest, like using that note packet and the things that are on there and just seeing if you can do it with that help. Okay. So here we're going to use these ideas to find values of sine and cosine of 2x. So we know that tangent of x is -3/4, and we know that x is an angle in quadrant 4. Oh, Roman numerals. So somewhere over here, that's where our angle is, right? And with tangent, you can think about these as being the sides of that triangle, right? Is 3 the horizontal side or the vertical side? Tangent is usually sine over cosine, right? And sine is the y. Does that make sense? So sine being the y means that, where does that 3 go in the triangle? The vertical side? And where does the 4 go? And if you want to be completely correct, maybe we should say that that's -3 because, it is down. Okay. And how could you find the length of the remaining side?
It's 5.
It's 5. It's a Pythagorean triple, but if you weren't sure, you would do -3 squared plus 4 squared equals c squared. You get 25 equals c squared, and c is 5. Okay, so we want to find sine of 2x. Now here's a question. Does doubling the angle double the sine? The answer is no. So like, what I'm asking you is sine 2x equal to 2 sine x? Is that true or false? It's false, and here's a really easy explanation. If you found, say, sine of pi quarters and multiplied it by 2, what do you get? What is sine of pi quarters? Radical 2 over 2, so that gives you root 2, right? Versus, what if I put that 2 inside with the pi quarters? That gives you sine of pi halves, which is equal to 1. See, those are not equal, okay? So what that's telling you is that numbers don't factor out of signs, the same as signs don't distribute, okay? So instead you have to use the fact that sine of 2x is equal to 2 sine x cosine x. That we proved in example 1. And so if you know that this is true, can you from that triangle figure out sine x and cosine x? I think you can, right? So sine of 2x will equal 2 times. So using that triangle, what is sine of x? Negative 3 over, over 5. If it were a unit circle and the hypotenuse were 1, then you could just have said it was negative 3. Or you could take that triangle and to figure out the sides and divide it all by 5, and then you would be able to look at just the x and y sides of it. How about cosine of x? That'll be 4/5. So sine of 2x in this case is, okay, 3 times 2 is 6, 6 times 4 is 24. So I think it's negative 24/25, right? Does that make sense? And actually, this number must be between negative 1 and 1. Why?
The domain.
Wrong. You're close, but it's the wrong word. It's because of the range. So see, what you did is you found sine of some angle, right? When you input an angle into sine, the outputs are always between negative 1 and 1, right? So since there was no number in front of this sign, right, that means that the output ends up being between negative 1 and 1 always. Does that make sense? Okay, so we know that sine of whatever that angle is. Notice how we didn't actually have to know what the angle was to figure that out. Does that make sense? Okay. All right, then let's find cosine of 2x. And there you can use any of those formulas we had on the last page. I am just going to use the fact that it's, let's use the fact that it's cosine squared x minus sine squared x. But any of them will work. So what was cosine of x? Just 4/5, yep, and that would be then squared, right? What was sine of x? And then we're going to square that. So the negative, if you forgot it there, it wouldn't matter, but that's just because you're lucky, right? So that will be 16/25 minus 9/25, and oh, they already have a common denominator, yay!
So why did we end up squaring them the first time? Like the cosine squared x and minus sine.
They're two different
Did-
identities.
Did you miss example 2? Okay, so go back and look at example 2. Example 2 gave us a formula for cosine of 2x.
Oh, right.
Okay.
Sorry.
It's okay, no, it's all good. It just wasn't clear if you were here for that, actually came in a little bit late, yep,
I got that end of it.
yep. If you can't see, you can also move your desk over, like I don't care as long as you move it back eventually.
Oh yeah, I can just do more from here, just there you go.
Okay. All right, so what is 16/25 minus 9/25? I think it's not 5, I think it's 7/25. But I actually often make the same subtraction error. So yeah, just the things to remember, guys, is that these two things, remember that sine of 2x is 2 sine x cosine x. That's something you're gonna have to use, so put that in like a big box, circle it in red, whatever you've gotta do. And then also that cosine of 2x is either cosine squared x minus sine squared x. I don't even have them all memorized. It's 1 minus 2 sine squared x, or it's 2 cosine squared x minus 1. Those are the things you're going to have to be using. And the reason that the cosine identity has cosine squared and sine squared comes from the things we had yesterday. So what these allow you to do is take an angle that's doubled and then half it. Does that make sense? Okay. So those are called the double angle identities because they give you identities for an angle that's double one of the others. So now we're going to derive half angle identities. Okay? You ready? Okay. So this is one of the ones that I wrote on the previous slide, right? Yes? Okay. So we are going to use this to find an identity for sine of x over 2. So how we're going to start is we're just going to replace m, R-E-P-L-A-C-E, replace m by x over 2. So first do that. Cosine of 2 times x over 2 equals 1 minus 2 sine squared x over 2. Is that part okay? And what to choose to replace things by is a little bit, sort of takes a little bit of finesse and practice to get used to, but for now I just want you to understand where these things come from, not necessarily do it on your own, okay? What happens with that 2 and that x over 2? The 2's cancel, and you get cosine of x equals 1 minus 2 sine squared x over 2. And if you want to derive, that kind of is mathematically a fancy way of saying find, you want to find an identity for sine of x over 2, you've got to get that sine of x over 2 by itself. Does that make sense? So what would be the first thing you would do to start that? Subtract 1, great. So cosine x minus 1 equals negative 2 sine squared x over 2. Awesome. Next, divide by negative 2, but yes. Cosine x minus 1 over negative 2 equals sine squared x over 2. Okay, it's often the case that people, instead of leaving the negative in the bottom, what they're going to do is this. They're going to say 1 minus cosine x over positive 2 equals sine squared x over 2. Does it make sense where that came from? That if I either multiply the numerator and denominator both by negative 1, or if I divide them both by negative 1, that's what I get. Okay, so I'll just write in like times by negative 1 times by negative 1. That's where that comes from, okay? And then what's the last thing you've got to do to get sine of x over 2 by itself? Take a big old square root. 1 minus cosine x over 2. And the one tricky thing is when you add in a square root sign, what else do you have to add in? Plus or minus. And you choose plus or minus based on what quadrant the angle is in. Does that make sense? So what you're gonna be asked to do is to find an angle, find sine of some angle. So your first step is to sketch what quadrants it's in and figure out in that quadrant is the sine positive or negative. Yeah.
How come, cause you use the square root to get rid of the sine squared?
Uh-huh.
How come it didn't touch the x over two?
How come it, oh, because it's kind of like when you have x plus 5 squared and you square root that, it just kills off the squared and doesn't touch the x plus 5.
Oh, okay.
Does that make sense? It's the exact same idea. Okay, awesome. Example 7 is doing the same thing for cosine, okay? So how about you give it a try? Like plug in x over 2 for m, solve for cosine of x over 2, just try it and see if you can figure it out.
Example 6.
Oh, did I renumber them? Example, I took one out. Yes, I mean the next one, whatever the next example is. So sorry, I edit my notes as I go, and I should make more notes to myself when I take out an example. So do it the same way. Plug in x over 2 for m, and then solve for cosine of x over 2. Just give it a try.
So the one on the board, not example 7.
Yeah, the one on the board, which in your page should be do example 6. The next one on the slide. Did you guys get cosine of x over 2 is plus or minus 1 plus cosine x over 2?
Mm-hmm.
Okay. That was even a bit easier because there wasn't that whole negative thing to mess with, right?
So the previous question, that was what the answer was the plus minus?
The answer wasn't the plus minus and the rest of the stuff, right? Okay. Does that make sense so far? Okay. And it's pretty similar to the previous one, except for instead of being, this one's 1 plus cosine, the other one's 1 minus cosine, right? Like they're awfully similar. How do you think you're gonna get a formula for tangent? How is tangent related to sine and cosine in the most basic fundamental way? Sine over cosine. So tangent of x over 2 is sine of x over 2 over cosine of x over 2. That identity is true as long as the angles inside the sine, cosine, and tangents are all the same, which in this case is x over 2, right? And then do you have an identity for sine of x over 2? We just found it, didn't we? So that was plus or minus square root cosine x plus 1 over 2 divided by plus or minus square root 1 minus cosine x over 2, right? Oh, I have them flipped. Oh, crap. Oh, no. Thank you for telling me. So sorry. So sine is 1 minus cosine of x over 2, and cosine is the plus 1. There you go. Phew. Is everyone okay with what I did there?
The square root is over that whole fraction.
The square root is over that whole fraction, yes. Yep. I'll try to make it obvious when it's not by doing stuff like making the fraction bar extend past the sides of the square root sign. Does that make sense? Okay, so is it clear that the whole over 2's can go away? Does that make sense? Because there's a 2 in the denominator of the numerator and the denominator of the denominator, right? You could just, that really is a square root 2 because it's square rooted, right? But you could multiply by root 2 in both numerator and denominator go away. So the first thing is that this is plus or minus root 1 minus cosine x over plus or minus root 1 plus cosine x. And here's the one tricky thing. Those plus minuses don't cancel. And there's a reason why. This means take positive the root divided by positive this thing, which makes a positive 1, right? Then do negative this root divided by positive that thing, which makes a negative 1. Does that make sense? So what that whole plus minus division is doing is it's doing a positive over a positive over a negative, and then it's doing a negative over a positive, and it's doing a negative over a negative. So the question is when you do those calculations, is the plus minus completely gone, or is there still a positive negative option? It's just on the outside, and there is just one of them, but the point is they don't cancel, okay? And then you can also write this as one big old square root sign, like that. Answer.
So I thought that if you changed the square roots to the quantity to the 1/2, I thought if you divide by, when you're dividing exponents, subtract.
If you have the same expression inside of the things in the first place. So in order to apply the exponent rule you're thinking about, you have to have something that's, say, like if you had 1 minus cosine x to the 1/2 over 1 minus cosine x to the 1/2, then you could subtract those exponents. What's the problem here? They're not the same. So what this is kind of saying is like if you had x squared over x, you can simplify that, right? But if you had x squared over y, you can't simplify that. And so that's the same idea here, is that even though the expressions look very similar, the fact that one is 1 plus and one is 1 minus means that they're actually really different. Similar, but not the same enough to apply exponent rules. So only could you do that if they were the exact same expression. Good question. Okay. So now we're going to use these things to find sines and cosines and tangents of angles that do not exist on our units, well, that do not give us nice numbers and aren't on our unit circle immediately. So here, yesterday we were able to find sines and cosines of angles by expressing them as sums of things that were on the unit circle, right? Like we said, okay, 75 is 30 plus 45, and I can, do sine and cosine on those two angles. Here, 165, this is half of an angle, So what is 165 multiplied by 2? 330. This is the same thing as sine of 330 divided by 2. And so a good way to check and see if you can do this is say, okay, well, if I double my angle, do I get an angle that I can work with? Does that make sense? Okay, and so then what we're going to do is we're going to use the sine formula, and that would be example number 5. What do you plug in for x? 330, exactly. Because in example 5, what you found is that sine of x over 2 was equal to plus or minus the square root 1 minus cosine x over 2, right? So sine of 330 over 2 is going to be, I'll leave the plus minus off for a second, 1 minus cosine, what goes in there? 330 over 2. And then the question is plus minus, which one? So I said you're supposed to look at your angle, 165. What quadrant does 165 fall in? The second quadrant. It's somewhere over there. In that quadrant, is the sign positive or negative? Sign is positive, so we take plus. So look at your original angle and find what quadrant it's in. Does that make sense? Okay. And then using your unit circle, you say, okay, cosine of 330, what is that? So on the unit circle, what quadrant is 330 in? 4. And it is 30 degrees shy of the axis, right? So at that particular angle, the x is root 3 over 2, and the y is negative 1/2. So that's going to be, for us, it's 1 minus root 3 over 2, all over 2. Does that make sense? Yes.
I made this more complicated than it has to be, but I'm just wondering if you could use 5 pi over 6 for x instead.
You could use 5 pi over 6 for x. Yes, and then you'd have to say that, wait, no, I don't think it's, you're saying 165. No, I think, well 330 is 11 pi over 6. So there's a reason that this book chose to use degrees, because they're a little bit easier to work with. But the angle that you plug in for x is 330, right? So the point, I think that what you're confused, I don't think that 165 is 5 pi over 6. Is it?
Yeah, because it's 15 above the axis, so double that would be 30 degrees would be your reference angle.
That's not supposed to be true. What?
You have to be 30 above.
Exactly, you gotta be 30 above. Okay, perfect, thanks. In your unit circle, this distance is 45, right? And then, I'm just gonna draw it really big and I'm gonna erase it. So you have this angle, and this angle, right? And my picture sucks, but the distance from these to these is 15, but from there to the axis is actually 30 degrees.
Yeah, and so like 165 is half of the bottom one.
I still don't get it.
Because 165 degrees is 15 above the x-axis, which is half of.
Can we? No, you're actually not right. Okay, I'm not trying to be like mean, but you're not right. So this is 90. What's the next angle in the unit circle we look at? It's 30 more, right? So what is it? 120. Then we have 135. What's the next angle then?
150.
150. And then we take a break until we get to 180. So 150 degrees, that is 5 pi over 6.
Yeah, so could you use that for x?
No. You can't use that for x. Yeah, so x is always going to be double this angle. Okay, so double that 165 is 330, right? So if you want to use radians, you have to have an equivalent of 330 in radians.
Okay.
So, yeah, so the answer is no, you can't. Oh, man, sorry. Okay. So this is the same thing as, how can you get rid of that whole like over 2 business? What if I multiply by 2 and multiply by 2? Will that do it?
Yeah.
Yeah, so that'll be 2 minus root equal 3 over 4. And that's kind of as the best you can do with this. We've got a radical inside of a radical. It's not a nice thing.
So like for real, I got that same answer using 5 pi over 6.
That's because you're lucky.
Okay.
Okay, I mean, it's not because it's right.
Okay.
So that sometimes will happen because there is a lot of repetition in the unit circle, right? And so I don't think that your method will always work. Okay, I do think if you want to use radians, just remember the fact that the relationship here between the x's and degrees was that the angle doubled, or the x is double what the angle is, right? So I think if you can use that, you're fine with using radians, and I applaud you for trying to use radians because they're more complicated. I think it might be easier to stick to degrees, just because. Okay, so how about tangent 105? So what's 105 doubled?
210.
So that's the same thing as 210 over 2. So what do we plug into our tangent formula? X equals 210. And that was into example number 7, right? Okay. So it'll be, oh, and let's figure out 105, what quadrant is it in? It's in the second one. It's 15 past. I think that's always going to be true, but it's always, the ones that you can do are always going to be 15 past an axis because you can find the things halfway between the 30 degrees there. So it'll be positive square root 1 minus cosine of 210 over 1 plus cosine of 210. And okay, 210. That is 30 degrees past 180. And so this part of the triangle is a half. That part's root 3 over 2. So that's the point root 3 over 2 negative 1/2. Okay. 1. So what goes in for cosine? Does it make sense it's going to become plus root 3 over 2? Because cosine and sine are both negative in that quadrant where 210 lies. Over 1 minus root 3 over 2, right? So how could you simplify that a little bit? Times by 2? So 2 plus root 3 over 2 minus root 3. And Alex might make you rationalize inside that big old square root sign. So if they do, what do you have to multiply by? 2 plus root 3. 2 plus root 3. Whew. And if we do that, got a big old square root sign. 4 plus 4 root 3 plus 3 over 4 minus 3. Actually, simplifies kind of nicely, doesn't it? So I think that's square root 7 plus 4 root 3. I think Alex will make you rationalize. Anybody come up against these kind of questions yet that has made it? Dane, have you seen any questions that make you rationalize? Not yet, no. Okay. If you don't have to, great. If you do, awesome. Yes?
How come the whole radical is positive?
Because the original angle was 105.
Yeah.
Oh, shoot.
Wouldn't it be negative?
No, I'm a dodo. It's negative. Yes, I'm so sorry. Why was I wrong? Why should this have been a minus sign?
Because it was a cosine.
Because it's tangent, and tangent is sine over cosine, and in quadrant 2, that's negative. I'm so sorry. Yes, that should be negative. So yeah, sorry. I was stuck on the previous problem where it was a sine. Because the angle of 105 is in this quadrant. And in that quadrant, remember that tangent is sine over cosine, and so since the cosine is negative, the tangent is as well. That was my bad. Thank you for asking. Okay. Is everybody good? Can I close this PowerPoint off? We're gonna start the next one as well, so just, you can't leave yet.